So good afternoon, everyone. Thank you for the invitation to present in this seminar series. I've been following it since its beginning a few years ago, so it's a great pleasure for me to have the chance to talk here today. Thanks also to Timothy and Valentina for their great talks about analog modeling. Of course, I'm also going to show you analog models, but also numerical ones that we have run in order to study the evolution of a very peculiar triple junction, which is the Afar RRR junction. So why is the Afar triple junction so interesting? Well, that's because out of all the triple junctions that we have available on our planet, and out of all the RRR, where R stands for ridge, and the nomenclature defined in the reference paper by Mackenzie Borna back to the 60s, Afar is the single RRR junction that is directly available for our observations on the surface of our planet. In fact, it is still above the sea level, while all the others RRR junctions are located below sea level. So it is directly accessible, and it provides direct input for our models and can be directly compared with our models. Of course, the Afar junction is there in the center of the yellow circle. And if we go to look a little bit more closer, we see that it is located at the junction between the Arabian, the Somalian, and the African plate. There are several models explaining its evolution, and this is an aspect that we want to test. But if we check the literature, we see that the evolution of this junction is related to the movement, the incipient movement of the Arabian plate back to 25 and more million years ago, that started to diverge with a northward direction, followed about 16 million years ago or later by the divergence of the Somalia and African plate. Nowadays, the Arabian plate moves northeastward with a velocity of 20 millimeters per year, while the Nubia and Somalia divergence in the central sector of the main Ethiopian rift, which is the southernmost branch of the triple junction, is about 5 millimeters per year. I mentioned that we refer to the RRR junction, so to the ridge nomenclature, but I should also mention that the situation here is a little bit more complicated, because we are not exactly in the presence of a ridge junction, but we are in the presence of a ridge rift junction. In fact, the Red Sea and the Gulf of Aden are already in an advanced stage of oceanization, more for the Gulf of Aden, a little bit less for the Red Sea, of course. But the main Ethiopian rift is still in its continental rifting stage. Okay, this is not a problem for us, because with our models, as you will see, we will start to investigate the process since the beginning. So we will talk about rift junction, and then if you push the model forward, you can reach the ridge state. As said, we have run analog models and numerical models with similar setup in order to to have comparable results and to confirm or disconfirm the outcomes of the analog models. I have to say, of course, that I'm an analog modeler, so I will focus my presentation more on the results deriving from this side of the modeling, and that for the numerical modeling, I relied on a great research team. Some of them are here attending and organizing the seminar series, so you know them very well. I have a slide at the end to thank all of them, so I will not spend more time now. But what I can say is that we started for designing our setup from the Mackenzie and Morgan reference paper, and we selected the most simple case for an RRR junction, so where we have the rift branches trending with 120 degrees. So in a very symmetric geometrical design. Here you can see the setup both for analog models and numerical models. Numerical models were run with the Aspect software. They are more or less similar in terms of parameters and in terms of vertical layering to the analog modeling counterpart. The difference is that, of course, the boundary conditions are a bit different, and that the scale is, of course, indeed very different. Numerical models can be run at 1-to-1 scale with nature, while our analog models were run with a scale ratio that is 1 centimeter the model equals to 20 kilometers in nature. All the other parameters were set the same. So we have two experimental series, one that is called symmetric and one that is called asymmetric or orthogonal. And the difference is in that in the symmetric experimental series, we have the divergence direction of the plates that is very symmetric, 120 degrees, again, like the trend of the rift branches. You see it in the panel A. While in the orthogonal or asymmetric experimental series, we have imposed an orthogonal extension on the southernmost rift branches. We have, of course, 3 moving plates that are connected in the analog models by an elastic membrane, and we can define a reference moving plate, which is the MP1, so the northernmost one that you can see has the Arabian plate, okay? While the other 2 plates are the Somalia and Nubia plate. In terms of vertical layering, we have above this hardware, this hard setup, so the moving plates, we have a viscous layer composed of silicons and dense sands in order to increase the density. So with this we simulate the lower crust, and then we have a brittle portion of the model on top of it that is built with sand mixture in order to simulate the upper crust. I should also mention that we have run models with a single stage of deformation and a double stage of deformation. In a single stage model, we have all the plates moving contemporaneously, and then in the double stage models, we have first the reference plate, the MP1, moving alone, and then in the second stage, we have also the other 2 plates that joins the movement, and so the plates keep moving all together. The last and most important parameter that we have investigated in this experimental series is the velocity ratio between the moving plate. The velocity ratio is a simple concept. We have defined it by considering the velocity of the reference plate that is always the same in all the models, and is 1 centimeter per hour. And then the velocity of the other 2 plates, which is the same for MP2 and MP3, but it can be half or a quarter the velocity of the reference plate. So an high velocity ratio like equal to 4, it means that the reference plate moves 4 times faster the divergence velocity of the other 2 plates, while a low velocity ratio means that all the plates, for example, if their R value is 1, moves with the same velocity of 1 centimeter per hour. If we mix all these parameters, we end up with a large amount of models. So I'm not going to show you all of them. I'm simply showing you the end members. So I'm going to show you the symmetric end member and the asymmetric end member. So models that are run with the most symmetric conditions and the most asymmetric conditions. You see in this table the parameters, so in terms of deformation stages and velocity ratio. I'm going to summarize them when we describe the models. And I'm going to show you the analog model and, of course, the numerical counterpart. Let's start with the most symmetric model. These models were run with a velocity ratio equal to 1, so it means that all the plates have the same velocity. A single phase of deformation, that means that all the plates move contemporaneously, and then with a symmetric direction of extension. So divergence is at 120 degrees for all the plates. If we look at the results and we look at the beginning of the deformation, we see that we develop both in the analog models and in the numerical models a Y-shaped, of course, geometry for the rift branches, but most important, at the center of the model where the triple junction is going to be localized. So in this sketch here on the left is the area that has the maximum subsidence, so blue colors. The faults coming from one rift branch and propagating toward the center do not interact to an high angle with the faults propagating from the other rift. This is more clear if we look at more advanced stages of deformation. And at the end of the model, in fact, you can see that the faults that come from one rift branch link completely link with the faults coming from the other rift branches without intersecting to an high angle. So this defines a perfectly symmetric triple junction and defines a Y-shaped geometry. That will be our symmetric end member. As you can see, results for analogs and numerical models are quite similar. Okay. If we check the asymmetric counterpart, we will see that there is quite a bit of a difference. This model in particular was run with a air ratio that is high, it's 4, so it means that the velocity of the reference plate is 4 times higher than the velocity of the other 2 plates. It was run with 2 deformation stages, and then the extension direction was imposed orthogonal for what concerned the third rift branch, the southernmost one, as you see in the sketch. So these are the results of the first phase of deformation when only the reference plates move northward. And what is important to highlight here is that at the junction between the 2 rift branches, what we get both in the analog and in the numerical model is a fault pattern that sees faults trending east-west. This was absent in the other symmetric model. But the interesting thing is that when we start to develop in the second phase of deformation also the third rift branch, these propagate northward and intersect the other 2 rift branches. Most important, the fault propagating from this third rift branch intersect the east-west trending faults derived from the first phase of extension to an high angle. And this defines basically a very symmetric fault architecture with faults intersecting to high angles and defining a T-shaped fault pattern. These are the 2 end member, of course. We have the full picture also for the intermediate case, because we have run all the models with the intermediate parameters. So we can see that there is a gradient of asymmetry that goes from the most symmetric single phase model to the most asymmetric double phase model with a high velocity ratio. You can see a summary in this picture. What is important to highlight from this picture is that we can see by running the full variety of possibilities in our models is that the key parameter for generating an asymmetric triple junction with T-shaped fault architecture is the differential velocity, so the air value, the air ratio. In order to have a T-shaped deformation full pattern, the triple junction, we need to have much higher velocity for one of the 3 plates. Then, of course, also the kinematic of extension, so the direction of extension imposed on the 3 rift branches and the number of phases play a role in this, but the key value we have seen that is the velocity ratio, the differential velocity. This is important when we go to check and compare our models with nature, so with the Afar triple junction. It is not by chance that we select as a best fit model the model with the most asymmetric setup, so the last end member that I've shown you. In fact, this approximates quite well the condition occurring at the triple junction, and we can see that if you compare the fault pattern in nature with the more analog model, we do have this T-shaped fault pattern occurring at the location of the present-day triple junction. We also see that this has migrated through time. I don't have time to discuss this in detail, but we do see a propagation of this triple junction through time in our models, like it is occurring in nature. And we obtain this T-shaped fault pattern migrating northeastward, of course. It is even more clear that there is a nice fit between this model and nature if we compare the displacement vectors for the particles in our model that we can derive from particle image velocimetry. This is a methodology that I haven't described for reason of time, but basically gives you, it allows you to track the movements and the velocities of your particles in the model, and they can be seen as GPS in nature. Okay, so if we compare these vectors derived from the models and the GPS vectors, we do see, as I hope you can also see in this picture on the left, that there is a straightforward correspondence in terms, of course, of relative magnitude, but also most important in terms of directions. The last degree of comparison, that I think is a nice degree of comparison, is given by the direction, the opening direction of the dikes in nature, and the t-axis that corresponds in nature to the sigma 3, the minimum horizontal stress, so it is orthogonal to false, basically, and the same parameter in our model. So if you compare the trend of these segments that correspond to the d-axis in the model, the t-axis derived for nature by earthquakes, and the dike opening direction, we do see a straightforward correlation. This suggests that the Afar triple junction, according to what our model say, should have developed with high degree of asymmetry. So multi-phase of deformation, orthogonal condition of extension, most important, high differential velocities. Okay. I want to conclude this presentation by thanking all the people that contributed this work. You can see their name here. And I just still another few seconds in order to invite you, if you work on these kind of topics, to consider the submission of your work to a research topic, so a special issue that we have recently launched in Frontiers in Neuroscience, with James Moorhead, Miriam Reyes, and Adina Puzuk. So submissions are welcome, of course. Thank you, everyone, for listening.
Thanks very much, Daniele. So I open the floor to questions. So I can ask a question in the meantime. So you showed your the map showing the t-axes and the dike orientations, and they had quite sharp rotations in some places, especially near the triple junction. So, how does it work when you get to have sort of orthogonal normal fault systems operating, at the same time, rather than combined to form like an oblique slip? What are your thoughts on this process?
I should mention that here in the rectangle that you see, pointed at this moment, there is where we have diking intrusion, recent diking intrusion. So there, the axes are a little bit further. If you want to look at dikes that are located in a southernward position, that means that even if you are far from the triple junction, there you somehow have the interplay of the stress fields acting contemporaneously at the triple junction. So they are associated with the movement of Arabia, but you are closer to the area where you should reflect more the extension associated with the Somalia and African plate. So somehow we have this switch in the stress field that act contemporaneously, and that allow to explain why you have some odd orientation, let's say, of dikes, for example, in places where you would expect to have dikes oriented in the opposite direction.
Okay, thanks, Daniele. There's a question in the chat from Fola. Do you want to say it, or should I read it out?
There's a bit of noise where I am, so I appreciate if you can read it.
Okay, I'll just read it out. So Daniel, there's a question from Fola. Do you see any evidence for syntectonic bookshelf faulting at any phase of the triple junction development in your models?
Syntectonics bookshelf. We haven't looked at that, honestly. I should go back to the models and have a look. It might be because we see some sort of sliding and rotation at the new date, maybe with PIV. Reanalyzing the model with a three-dimensional PIV could provide some more insight into this aspect. I would expect I would expect this behavior because especially where you have higher deformation. So in models where, like not in the last one that I've shown, in which for the main Ethiopia rift, for example, you don't have such a big deformation. But in models where the deformation is higher, you do see some fault rotation that may reflect the behavior that you are mentioning. So definitely, I would say yes.
Thank you.
Welcome, Foreign.
I think, Kathy, you've put a question in the chat. If you want to, we've got time if you want to ask it.
Yes, it was really following on from your question, Derek. Do you hear me?
Yep.
Yeah, okay. And it's whether, I mean, those sort of patterns that are shown in this image we're looking at now remind me a little bit, and I may be remembering them wrong, the seismic anisotropy fast directions as well. And I wondered if there was anything relevant to that in the analog modeling, or whether that seismic anisotropy information is primarily reflecting magma-assisted rifting, which is not clearly what you're modeling here.
Yeah, it's hard to say, especially considering analog modeling, because, I mean, as you know, analog models are not the best at reproducing, for example, magma-assisted rifting. This is one of the limitations, so it's hard to say basing on the analog models. Yeah, I must admit this.